Hi, myself Dr. S.K. Bosho, former HOD, Department of Physics, Cotton University. This is a video lecture in physics for class 12 students, and the topic is electrostatics. Chapter 2, Lesson 4, Capacitors and Capacitance, Part 1. In this lesson, we will consider capacitors, then parallel plate capacitors, then effect of dielectrics on capacitances, and finally, energy stored in a charged capacitor. Let's begin. Basic concept of a capacitor. Consider a positively charged but completely isolated conducting sphere. Its potential is, with usual notations, V plus dash equal to 1 by 4 pi epsilon naught Q by R. We call it equation 1. Similarly, the potential of a negatively charged but completely isolated conducting sphere is V minus dash equal to minus 1 by 4 pi epsilon naught Q by R. We call it equation 2. Let us compare V plus dash and V minus dash with respect to the potential of an infinitely distant reference point. As usual, the potential V infinity of the reference point has been assigned the value 0. The comparison is illustrated in the figure below. The potential difference between the spheres is V dash equal to, finally, 1 by 4 pi epsilon naught 2Q by R. Call it equation 3. The equation 3 tells us that the potential difference V dash is proportional to Q, the magnitude of charge on either sphere. The equation may be rewritten as Q equal to bracket start twice pi epsilon naught R bracket close V dash equal to C dash V dash. This is equation 4. C dash is a proportionality constant and is called the capacitance of the two spheres, where C dash is equal to Q divided by V dash. We call it equation 5. C dash refers to the charge holding capacity of the system of two spheres. Let us now look for ways to enhance the capacitance of the system. That is, the charge holding capacity of the system. We have learned that the potential of a charged conductor is the amount of work done in bringing a unit positive charge from infinity to a point on the conductor. Thus, V plus dash is the work done in bringing a unit positive charge from infinity to a point on the positively charged sphere. And of course, the transfer of the unit positive charge has taken place without causing any acceleration to it. The work done, V plus dash, will get reduced in presence of a negatively charged conductor because its attraction will partly offset the repulsion of the positive sphere on the unit charge. In other words, the potential of the positive sphere will decrease. Similarly, the presence of a positively charged conductor will increase the potential of the negative sphere. Let us reassess the potentials of the spheres in a modified circumstance. The potential difference is V dash when the conductors are infinite distance apart. The potential difference is V when the conductors are close together. What we have observed here is the reduction in the potential difference between the spheres, although the charges in the spheres have not changed. In other words, the capacitance of the system of two spheres has increased to a new value, C equal to Q by V. It is equation 6. From the previous value, C dash equal to Q by V dash, which was given by equation 5. With this much background, let us formally begin the topic, capacitors and capacitance. In fact, we are now ready for formal definitions of capacitors and capacitance. A system of two conductors separated from each other by vacuum or by some dielectric constitutes a capacitor. The conductors are referred to as the plates. A capacitor is also called a condenser. Instead of vacuum, we can say air, since the dielectric constant of air is equal to 1.00059, that is almost equal to 1, the value for vacuum. When connected to a battery, the plates acquire equal and opposite charges. Let V be the potential difference and Q be the magnitude of charge on each plate. Then the capacitance of the capacitor is given by C equal to Q by V. The capacitance is also referred to as capacity. As the name implies, capacitance refers to the charge holding or storing capability of a capacitor. Similarly, we may define the capacitance of an isolated single conductor. For such a conductor, the other plate may be imagined to be situated at infinity. For example, let us consider a conducting sphere of radius r. We imagine that the second plate is a concentric spherical cell of infinite radius. The potential difference between the sphere and the shell is, therefore, V equal to V minus 0, since the potential at infinity is equal to 0, is equal to 1 by 4 pi epsilon naught Q by R. Therefore, the capacitance of the sphere is C equal to Q by V equal to 4 pi epsilon naught R. The SI unit of capacitance is farad. The unit is named in honor of Michael Faraday, whose contributions to science includes his works on capacitance also. This is the photograph of Michael Faraday. 1 farad is equal to 1 coulomb per volt. Farad is a huge unit. The smaller but more practical units are microfarad, that is 10 to the power minus 6 farad. Microfarad or picofarad, that is 10 to the power minus 12 farad. The circuit symbol for a capacitor are shown below. First, for a fixed capacitor, this is the symbol. And if the capacitor is variable, then this is the symbol. The capacitance of a capacitor depends on shape and size of the plates, distance between the plates, presence of dielectric between the plates. The capacitance of a given capacitor may be calculated provided the above information are available. We'll soon see it in a context of the parallel plate capacitor. Also, we have various instruments to measure the capacitance of an unknown capacitor. Types of capacitors. Depending on the shape of the plates, we may categorize capacitors as parallel plate capacitor. The plates are two large plane parallel sheets. Spherical capacitor. The plates are concentric spherical cells. Cylindrical capacitor. The plates are coaxial cylinders. Parallel plate capacitor. As already stated, a parallel plate capacitor consists of two identical parallel metal plates separated by a small distance. The plates may be square, rectangular, or circular in shape. In the beginning, we take the space between the plates to be vacuum or air. Let A be the area of its plate and D be the separation between them. When connected to a battery, the plates get charged Q and minus Q, say. As the separation between the plates is very small compared to the plate dimensions, we may safely use the expression for electric field due to a uniformly charged infinite plane sheet. In between the plates, the fields due to the individual charged plates are additive and is given by E equal to E plus E minus equal to sigma by 2 epsilon naught plus sigma by 2 epsilon naught equal to sigma by epsilon naught. Here, sigma is equal to Q by A is the charge density and epsilon naught is the permittivity of free space. The field is uniform and is directed from the positive to the negative plate. For a uniform field, the potential gradient may be replaced with the potential difference divided by the distance. Thus, in magnitude, of course we know the direction. E equal to dV dx equal to delta V by delta x equal to V plus minus V minus divided by D, which is ultimately equal to V by D. V stands for V plus minus V minus. Here, V plus and V minus are respectively the potentials of the positive and the negative plates. Therefore, the potential difference between the plates is V equal to E multiplied by D equal to sigma by epsilon naught multiplied by D equal to Q by epsilon naught A multiplied by D. Therefore, the capacitance of the parallel plate capacitor is C equal to Q by V equal to epsilon naught A by D. This is the final expression. Remarks. The expression for the capacitance of a parallel plate capacitor tells us that its value depends on its geometry. Taking the Q, we may design a variable capacitor by arranging to alter the area of overlap between the plates. This is a photograph of a variable capacitor. Effect of dielectric on capacitance. We have talked about atomic/molecular dipoles and appearance of bound surface charges in a dielectric in presence of a nearby charged body. Please refer to Lesson 2, Chapter 1 on conductors and insulators and Lesson 7, Chapter 1 on electric dipole. We are now familiar with the concept of an electric field, so in partial modification to our earlier narration, we'll replace the charged body with an electric field. The field would polarize the dielectric by aligning the dipoles in its direction, a process that ultimately produces the surface bound charges. In the figure, the space between the plates of a charged parallel plate capacitor is completely filled with a dielectric. The electric field E of the capacitor polarizes the dielectric and surface bound charges appear. E dash is the field produced by these bound charges. E dash is smaller than E and is oppositely directed. The magnitude of the resultant field in the capacitor is therefore E subscript D equal to E minus E dash equal to sigma minus sigma B divided by epsilon naught. This is equation 1, where Sigma equal to Q by A equal to surface charge density in the plates. Sigma subscript B is equal to bound surface charge density in the dielectric. And epsilon naught is the permittivity of free space. In a linear dielectric, the bound surface charge density is proportional to the incumbent electric field, which in turn is proportional to sigma. Now, what is a linear dielectric? A dielectric is linear if its polarization is proportional to the applied field. Thus, sigma minus sigma B is proportional to sigma, and we may write sigma minus sigma B equal to sigma by K is equation 2, where K is a constant called the dielectric constant of the dielectric material. It is also called the relative permittivity epsilon R. Combining equations 1 and 2, we have ED equal to sigma divided by epsilon naught K. Therefore, potential difference across the plates is VD equal to ED multiplied by D equal to sigma D divided by epsilon naught K equal to QD divided by epsilon naught Ka. This is equation 4. Therefore, capacitance of the capacitor in presence of the dielectric is CD equal to Q divided by VD equal to epsilon naught Ka divided by D. This is equation 5. And the final expression for capacitance of a parallel plate capacitor, where the space between the plates is entirely filled with a dielectric of dielectric constant K. Thus, the presence of the dielectric medium in the space between the plates increases the capacitance K times, K being the dielectric constant of the medium. In the first figure to the left, parallel plate capacitor without the dielectric, the capacitance is C. To the right, the same capacitor with a dielectric in between the plates, and the capacitance has increased to a new value K times C, C being the original value. Equation 5 may be expressed as CD equal to K epsilon naught A divided by D equal to Kc. Equation 6. Or K equal to CD divided by C. This is equation 7. Equation 7 is valid for any type of capacitors. Moreover, equation 7 may also be regarded as a definition of dielectric constant of a material. Now, energy stored in a charged capacitor. A capacitor is charged when its terminals are connected across a battery. Electrons from the plate connected to the positive of the battery are transferred across the external circuit to the other plate until the full charge is achieved. Now, what is full charge? For an applied potential difference of phi, the full charge is Q equal to C phi, where C is the capacitance of the capacitor. Although the process takes place instantaneously, we'll break it down to a step-by-step process for the sake of understanding. Also, we'll describe the charging in terms of transfer of positive charges instead of electrons for the sake of an uncomplicated narration. Late, at an intermediate stage of charging, the charge developed in the plates B, Q and minus Q respectively. Here both the Q's are small q's, and the resultant potential difference across the plates B, V. V is small v. Now an infinitesimal amount of charge dq is transferred from the negative to the positive plate. The work done in the process is dW equal to small v dq. Q is small q. Substituting small v equal to small q divided by C, where C is capital and C is the capacitance of the capacitor, dW is equal to small q by capital C dq. Therefore, total work done in the process is W equal to integration dW equal to integration 0 to capital Q small q dq divided by C equal to half capital Q square by capital C, where capital Q is the full charge. If capital V is the potential across the plates at a full charge, then W equal to half capital C square capital V square divided by capital C equal to half capital C V capital square. The work done in the process is stored as the energy of the charge capacitor. If the charge capacitor is short-circuited, that is, the plates are connected by a metal wire, the capacitor will discharge and the stored energy will be liberated in the form of heat energy. The energy gained by the capacitor during the charging process is at the expense of the chemical energy of the battery. A point could be raised here. Why did we carry out the integration while calculating the energy stored in a capacitor? Well, the answer is this. The integration was necessary as the potential difference across the plates continually increased during the charging process. We have come to the last topic of the present lecture, energy density of an electric field. Let us calculate the energy stored in a charged parallel plate capacitor. We'll be using usual notations. The energy stored W can be shown to be equal to half epsilon naught within brackets sigma by epsilon naught whole square into A into D. Now sigma by epsilon naught equal to E is the field in the region between the plates, and A multiplied by D equal to omega is the volume of that region. Therefore, W equal to half epsilon naught E square into omega. Therefore, the energy stored per unit volume in the region between the plates of a parallel plate capacitor is U equal to W by omega equal to half epsilon naught E square. We may call U as the energy density of the electric field. Although the above result has been deduced with respect to a parallel plate capacitor, the result is universal for any electric field. This brings us to the end of the lesson 4 of chapter 2. We'll pick up series and parallel combinations of capacitors in the next lesson. Till then, goodbye and thank you.